Hi, everyone. My name is Christopher Jung. I'm currently a fourth year PhD student at Penn, where I'm fortunate to be advised by Aaron Roth and Michael Kearns. And today I'll be talking about an algorithmic framework for fairness elicitation. And this is a joint work with Aaron Roth, Michael Kearns, Stephen Wu, Logan Stapleton, and Seth Neel. In the rest of our time, I'm going to talk about the motivation for this work and then formally state the problem and then share some of the results that we have. First, I'll talk about the motivation for this work. In the past few decades, as there has been a lot of interest in algorithmic fairness, by now we have a lot of fairness definitions. But a lot of these fairness definitions are maybe a little bit too simple and reductionistic. And what I mean is that a lot of them can be simply boiled down to equalizing some statistic of the predictor across different groups. So in essence, in order to define what fairness is for a specific context, it boils down to choosing which statistics you're interested in for the specific predictor, and what are the groups that you want to equalize this statistics across. But by now we know that a lot of these definitions are not compatible with one another. And this kind of begs the question, how should we go about choosing which fairness definitions to use? Meaning which statistic should we equalize and what are the groups that we want to consider? And I think that kind of misses some of the little nuances that the fairness contains. And in fact, because in reality, fairness may not be cannot be written down in as simply just equalizing some kind of statistic across different groups. And also by simply defining fairness only in that way, we might not be able to actually incorporate a lot of the domain expertise into these definitions. So the question that we were interested in this work was, can we try to elicit how stakeholders and experts within the domain viewed fairness? And meaning instead of reducing fairness into those simple abstractions such as equalizing some kind of statistics across different groups, we wanted to be able to learn how these people actually view fairness. However, it's actually a hard task for these people to be able to enunciate their conceptions of fairness. Meaning, if we ask the people, what is fairness? It's not clear how those people can answer that question in a very principled manner. Yet, it's actually easy for these people to identify specific scenarios where fairness or unfairness occurs. Meaning, if we provide a specific scenario and what has happened, the outcome of that scenario, they can either say, yes, that was fair, or no, that was not fair. With that in mind, we wanted to provide scenarios to these stakeholders and domain experts and ask them to make some kind of fairness judgments within that scenario. More specifically, in our case, the scenario consists of two individuals, A and B. And the fairness judgment that the person that we want to elicit fairness from has to answer is the following. They have to answer whether A and B should be treated similarly, or A should be treated as well as B, or B should be treated as well as A. And now, given a lot of scenarios and the subject's judgments on those scenarios, we wanted to be able to directly learn a classifier that tries to obey these people's judgments on those scenarios. And by framing fairness in this way, even non-technical domain experts can actually participate in voicing their opinion on how fairness should be viewed in these the domain they're expert on. Another approach would have been to actually just simply model how these people are making these kind of fairness judgments. So for example, in the case of individual fairness, maybe we could have learned what is the underlying fairness metric D. But in order for us to have any kind of generalization to unseen points, we actually need to make some kind of assumption about the structure on how these people are making these fairness judgments. But in our case, because we don't actually try to model how these people are making judgments, and we still have generalization because we're directly trying to learn a classifier that obeys these people's judgments on these different scenarios. Anyway, now let me try to formally state what the problem is. The setting that we're in, that we were interested in, is in the batch setting, meaning we're given a training data set that consists of person's features denoted as X and the person's label Y. And we also want to have some kind of elicited fairness from the subjects from whom we want to elicit fairness from. And to each subject, this is what we're going to do. We're going to show a list of random pairs A and B from the training data set. And then now we're going to form this list called CU for the subject U, where it consists of pairs A, B. And it is in this list if the subject U thinks that B should be treated just as well as A. And note that this actually encapsulates what we talked about in terms of fairness judgments in the previous slides, where if the subject thinks that A and B should be treated similarly, we can simply include AB and BA in this list. And if A should be treated as well as B, we can include BA in this list. And finally, if B should be treated as well as A, we can include AB into this list. Now, given those kind of list of pairs, we can kind of define what it means for predictors to incur fairness violations, violate those fairness constraints, or actually satisfy the fairness. So we're interested in soft predictors, meaning given some kind of a point X, it's going to output some score between 0 to 1. And we're going to say this predictor H incurs gamma fairness on the pair AB in the list if it's a case that HA minus HB is greater than gamma, meaning the difference between their treatment is more than gamma, meaning B is not being treated as well as A. And we're going to say the amount of gamma fairness violation is exactly this value, which is the difference between their treatment minus gamma. Now, given that, the problem that we're interested in, I can finally state what the actual problem that we're interested in is. We want to be able to find a predictor H that minimizes H such that the following holds true. For each pair that was included in some list CU for some subject U, we're going to keep track of the gamma violations via these variables called violations IJ. And then we're going to actually take the average of these violations and make sure that this is less than eta. And now I'm going to kind of talk about how we actually solve this problem. Note that the problem that I've just shown you before it's a constraint optimization problem where the constraints are actually linear in the predictors H. And instead of solving the constraint optimization problem directly, we're going to actually take a different perspective on this problem, where we're going to cast it as a min-max problem. So we're going to take the Lagrangian and try to solve this min-max problem between two players, where the learner is going to choose the predictor, and the auditor will just choose some kind of penalty weights across the constraints such that the learner will pay these penalties for any of the violated constraints. And now we're going to try to solve that min-max equilibrium through a no-regret dynamics. And first, instead of solving the min-max equilibrium, it's equivalent to solving max-min of the max-min equilibrium in this case, because the objectives are actually linear in all the strategies of the learner or the auditor. And so we're going to flip the order, meaning the auditor will go first, and we're going to have the auditor play some kind of no-regret strategy. And then learner will try to best respond to the strategy chosen by the auditor. And I'll quickly show you in the next slide how it can actually best respond through a cost-sensitive oracle. But the high-level idea of using this cost-sensitive oracle in this case is that the objective value, the Lagrangian that we want to consider, it consists of the error of the predictor and then the penalty that the learner has to pay for the violated constraints. But because the violated constraints are actually linear in terms of its predictors that are chosen, we can actually fold these penalty terms into part of the error and view that as some kind of weighted error for the predictor. And so this is the objective, or the Lagrangian, that we wanted to consider in the case of max-min problem that we were considering. The first term is the error across for the mixture of the hypotheses that were chosen. And the later terms are all the penalties that the auditors are choosing, where alpha indicates the violation of the pairs, which I denoted as violation ij in a couple of slides back, and lambda and tau are the actual weights chosen by the auditor. And so in order for the auditor who's choosing which lambda and tau to play, the auditor will do a projected gradient descent for one of the variables and exponentiate a gradient descent for the other variables, but it doesn't really matter what kind of strategy we were doing. As long as it's no regret strategy, we're okay. And we can easily do that because the above Lagrangian, they're actually linear in these penalty weights we're choosing. And after that, after the auditor chooses these penalty weights for the constraints, the learner has to choose a mixture over these hypotheses and also these violations term alpha, but that can be easily done through a cost-sensitive oracle because, as I mentioned before, these terms are linear in these hypotheses H, so they can be folded into the error term, and it boils down to finding a predictor that's trying to minimize some kind of weighted error. And let me share some of our results. We first show that the algorithm that I mentioned indeed finds the actual max-min equilibrium and polynomial time through these CS oracle calls. And we can show the actual optimal value achieved by our algorithm shown before is indeed approximately optimal. And even the constraints that we had, the fairness constraints we had are approximately satisfied. And here's a graph showing that even in practice, our algorithm indeed works, where all the learner starts off. So this is a graph showing what's happening during the no-regret dynamics. On the top right corner, that's where all the learners start. And then as the no-regret dynamic progresses, it converges towards to this point such that it actually satisfied the gamma that was actually specified for the optimization problem. So in this picture, we ran it with varying degrees of gamma. So gamma could have been either 1.1 or 0.9, 0.8, and so forth. And we ran the algorithms and made sure that the final algorithm is such that the max violation was indeed at most 1 and 0.9, 0.8, and so forth. And so I've kind of just described what the guarantees we can give for the empirical risk minimization problem. And now, but we also give a lot of guarantees for out of samples, meaning first we give accuracy generalization, and this simply falls out of, we simply appeal to a VC dimension way of bounding the error generalization through uniform convergence bounds. We also actually show our fairness generalizes, meaning we were trying to bound the average level of fairness violation beyond gamma over all the pairs to be less than eta. And indeed, if this value, even on unseen samples, will be the probability that will be a lot bigger than the specified level of eta will be pretty small. And let me make some comments regarding this fairness generalization. it's not as straightforward as the accuracy generalization. We cannot simply appeal to those VC dimension techniques. And here are some reasons. Note that the fairness loss that we're interested in is actually defined as an average over non-disjoint pairs of individuals in the sample. And second, the empirical fairness and true fairness loss, the difference in them, is not a convex combination of the supporting hypothesis. It's a non-convex combination of them. But we were able to kind of get around these kind of problems by first, instead of using Chernoff bounds during the two-sample trick of VC dimensions techniques, we used the McDermott's inequality to get concentration. And for the second problem of being the combinations, the difference in the empirical fairness loss and the true fairness loss not being convex combination of the supporting hypothesis, we get around that problem by using this epsilon net over these hypotheses with respect to these fairness losses. I think if you want to see more details regarding this thing, you can find the details in the full paper. Finally, I kind of wanted to share some of the preliminary experimental results that we had. We wanted to carry out this experiment with real human subjects. So we had 43 undergraduate students from a major American research university participate in this, where each student was shown 50 randomly chosen pairs from the COMPASS data set. And this is what they would have seen for each pair. They're given each individual, where each individual is represented by these different kind of data we have about them. And they had to indicate whether these two individuals should be treated equally or it was okay for them to be treated differently. And with that, we actually trained a bunch of different models subject to each of those subjects' constraints. Instead of combining all of them, we separately trained model under everyone's set of constraints. So we have H1 for the first subject, model H1, and then we got a predictor H2 in order to find these H2, which is the predictor that minimizes the error under subject 2's constraints, and so forth. And now, given this, we wanted to compare these different models by looking at their Pareto curves. And what I mean by Pareto curves, I mean the Pareto curve that visualizes the trade-off between fairness and error, where we had these slack parameters for fairness, the eta, gamma, and eta, meaning the smaller they were, we can kind of enforce how much the stricter the fairness constraints are. And so by kind of changing them, we can see how these models' accuracy changes as a result. And so for the purpose of being able to visualize this Pareto curves, we set eta to be 0, and we simply varied gamma and try to trace out what the actual, what the error changes look like. And this is what it looked like for those 43 undergraduate students who participated in this study. And as you can see, there is a lot of variability even amongst these students, meaning there is a lot of kind of variability in terms of how they viewed fairness. And we thought that maybe this is due to how many number of pairs they deemed how many pairs that they thought needed to be considered similar. So it's possible that some of them didn't actually say, oh, it's possible that the subject chooses no pairs to be treated similarly, and it's fine if the model does whatever it wants. And of course, the more and more constraints that are included in this set, the harder it's going to be for the predictor to satisfy that. But even accounting for the number of constraints, we see that there's still a lot of variability. So indeed, the more number of constraints the person included in their fairness constraints, the higher the error was. So indeed, there was a correlation of 0.68, but even then, there's still a lot of variability that gets explained away by the number of constraints. Anyway, that was it. If you want to see more details, you can find the full paper on on archive. And yeah, thank you for giving me your attention up until this point. Thanks.